Hello and welcome to Beamer, folks. I thought today we would explore the landscape of an op-amp. I particularly like this op-amp. There is, of course, a whole myriad of op-amps, but this one I've got to know over the years, and it's the TL072A op-amp with it's a JFET input, so very high impedance. As much as there are a myriad of op-amps, there's also a myriad of applications. I'm going to stick to one application, and that is a constant current sink and source. You can use a sink as a source and you can use a source as a sink, but I quite like the idea of an instrument being able to supply both, that is a current sink and a current source. The design I've come up with here runs on 12 volts DC. It has on its output a transistor BD139, a driver transistor of BC546, and a Zener diode reference. You can see the circuit here, it's circuit A. And what can you use? What can you use current sink sources for? There are many applications, but you can use it for battery charging, resistance measurement. You can put a resistor over a current in a current source, and the voltage you can translate into resistance. Laser diodes are very critical to current or voltage, I should say, and a slight increase in voltage could mean a massive increase in diode current, which would destruct the device. So having controllable current to the laser diode means that you have very fine control over the diode itself. You can check diodes with it, transistors with a current source, and of course you've got LED brilliance. LED brilliance is proportional to the current flowing through the LED, so a precise control over the current means precise control over the brightness, and many resistive type sensors. There are a number. I'll mention one here, which is a temperature device. If you have a constant current and you feed that into a resistive sensor, the temperature then becomes proportionate to the voltage across that sensor. That was just a small sample of the many uses, applications that you can put a constant current source to. There are many. Right here is the circuit that I designed, and I'll start off at the very beginning. We've got a supply voltage here of 12 volts DC. We've got a reference voltage here of 4.7 volts. Well, if you take 12 volts minus 4.7, that equals 7.3 volts. Now that's the voltage across R1, so you divide that by 750 ohms, and that comes out at 9.7333 reoccurring milliamps. So it's not really 10 milliamps, it's 9.73. Next you have a voltage divider, which I've set up here with a 39k. These are standard values, 39k in series with a 10k, assuming a very high impedance here on the positive input of the op-amp. This will produce a current of, well, we've got a reference voltage of 4.7, so let's go 4.7 volts divided by the sum of these two resistors, which is 49k, and that comes out at 95.9 microamps. So it's close enough to 96 microamps. That 96 microamps is taken away from the current flowing through the Zener diode here. So what is it, 9.733 milliamps? Well, 96 microamps of that is flowing through this resistive network. Just as a sort of sideways thought to a Zener diode, it's worth noting that it constitutes and represents a very simple, cheap device, which is actually quantum tunneling. So it's quite a remarkable little device. And how much they cost? About a penny. When were they invented? Many, many years ago, probably in the 50s, somewhere around there. But considering that this is a quantum tunneling device back then, it's quite a remarkable thought, isn't it? The op-amp itself, back to op-amps, is configured in a unity gain. So the voltage here, which is 0.96 volts DC, will be reflected directly on its output, and its output, whilst appears to be here, it goes through Q3, comes out of the emitter of Q3 and into Q4, and comes out at Q4 across R5. So what we should have in the practical circuit is, excuse me, is 0.96 volts DC across this resistor, and it should be exactly the same as the voltage across R3. When there is 0.96 volt across this resistor, and the resistor is 100 ohms, if you take the 0.96 and divide it by 100 R, you come up with a current of 9.6 milliamps. So this circuit will always maintain 9.6 milliamps. So if you present a load from plus 12 through to the collector of these transistors, you should always experience 9.6 milliamps flowing through this point here. It doesn't matter whether that is a small resistor or a large resistor or a diode, or indeed you can short these terminals out. You will only have 9.6 milliamps flowing into the collector of these transistors, and therefore that becomes a constant current load. There is one limitation, and that is the compliance voltage. The compliance voltage here is plus 12 volts DC, and so therefore your resistive value, if you use the resistive value as a load, would have its upper limit. The only way you would achieve 9.6 milliamps on higher value resistors is to increase this voltage here. Another thought worth considering, there's a couple of surprises in this, is that the TL072A cannot exceed a voltage of, I think it's 30 volts. 36 volts is absolute maximum, but you wouldn't really want to run this beyond 30 volts. So our supply can shift up to 30 volts DC without too much trouble. I thought I'd add that the minimum supply voltage of the TL072A is about 5 volts. I have run them slightly lower than that, but that is the theoretical minimum. So the compliance voltage here could move from 5 volts up to about 30, possibly 32 volts DC, quite a range. And whilst I'm at it, I think it's probably worth mentioning how the op-amp actually functions. In principle, it will do anything and everything it can to maintain the voltage from its positive non-inverting input through to the output. So for example, this is in a unity gain loop. So if let's say for example, the voltage on R5 went down, then pin 2 would naturally go down. As it's the negative, the output will therefore go up. If that goes up, the emitter of Q3 will go up, the emitter of Q4 will go up, compensating for the downward movement of the voltage, and it would be held locked. So if it were to go down on the inverting input of the op amp, the output would do its damnedest to make sure that actually the output here will go up to compensate for it. If we look at the positive input of the op amp, if this were to go up, then the output here would go up. If that were to go up there, the emitter would go up of Q3 and the emitter would go up on Q4. So the output will follow on pin 3, which is the non-inverting input. Whatever voltage is placed on here will be reflected directly to the output of Q4, which lends us to the thought that R3 could actually be a variable resistor. Okay, so the next thing for me to do is build this on a proto board and see how it works. This is Beamer signing out for now.